Hello, everybody, and welcome to the AutoCall Fire Detection Academy's webcast series. This is a new series of courses that's designed to deepen your understanding of some of the key features and technologies we have within the AutoCall product line, and to deliver a deeper set of knowledge and understanding than you would get out of the normal launch webcast. The launch webcast series is designed to bring awareness of the products and to help you understand the features, benefits, applications, but we recognize that once you really get into the product and start selling it, other questions arise that are usually around, how can I do this? Can I do this? Can I do that? And what do I do with the product once we really begin to apply it? So the idea of this session is to serve as a bridge between the launch presentations, which are at the 20,000 foot level, and coming to a full-blown multi-day class in a JCI Fire Detection Learning Center. So that's the plan for the program here. And we're going to kick off this today with a discussion about TrueAlarm detection. We'll look at the industry-leading features such as our competitive advantage in several devices, and finally, programming demonstration of several widely used TrueAlarm devices. My name is Brian Shifley, and I'm on the JCI North American Learning and Development Team for Global Fire Protection Products at Johnson Controls. I'm based out of Westminster with my team, and this is a team that I lead that are responsible to deliver our fire detection training to you either virtually or instructor-led in our classrooms, which are around the country. Today, hosting the event for you will be David Govin. David is a highly experienced senior trainer on the L&D team. Dave has many years of experience with our product lines in both the field and the classroom. Also supporting this webcast is David Henry, who will deliver the programming demonstrations of these devices. Dave is an experienced trainer and subject matter expert in all ES products and is qualified to deliver all of our technical training. I'm excited to have both Daves here as the experts to present this material, demonstrate the programming, and to answer your questions at the end of the presentation. So feel free to bring any questions you have regarding this content about the technology of it, its integration, and how it all fits together. So a couple of housekeeping items before we get started. Everybody in the session will be on mute in just 1 second, and mute all. Yes, there we go. So everybody's on mute. So if you go ahead and unmute yourself, what you're going to do is you'll be heard by everybody on the call, and then we'll have to go in and remute you again. But we cannot unmute you. You have to do that on your own when it's time for the questions. Something else, this session is being recorded. So if you have any concerns about your privacy or don't want to be recorded in this session, which will be published later to autocall.com in the product launch webinar section, I would recommend that you drop off the call now. So in terms of questions, we're going to do is hold the questions until the very end of the session, and then we'll open the floor. You can ask questions verbally using the microphone, as we mentioned earlier, or you can type the questions anytime via the chat interface here in Teams. Everyone will see the questions, and they too will become part of the recorded session. So with that, I hope that you enjoy the session, and I encourage you to participate by asking questions at the end of the session. So please, Dave Govin, please take it away.
Thanks, Brian, and welcome everybody to the AutoCall TrueAlarm live webcast. In today's webcast, we're going to talk about TrueAlarm detection and TrueAlarm concepts. So first, let's begin by talking about how the fire alarm system works with the inputs and the outputs. So on the left, we could have input devices such as heat detectors and sensors, smoke detectors, sensors, gas detectors and sensors, or some type of monitoring sensors like other items that get connected to the fire alarm system. In the middle, we have the central processing unit, which is the fire alarm system, which makes all the decisions, right? So if one of the input devices crosses the threshold and goes into alarm, the fire alarm control panel has to make a decision and control some type of output. Some of these outputs can be notification appliances such as audio visuals, annunciators, or maybe relays to control fans or door holders. And then the last thing would be sending a signal to the central station. So that's a basic, I'll call it, description of how the fire alarm system works in 3 separate, simple, easy pieces. So how do the addressable smoke sensors have advantages over conventional detectors? Well, they provide constant sensitivity adjustments on the fly. They support many devices on a single wire run, reducing the wire within the facility and the conduits that support the wiring, therefore reducing installation costs. They are individually programmable. So we can set a sensitivity for one area of the building different than another, which a good example of that would be a computer room, where the sensitivity levels have to be higher than the general areas of the building. And by having addressable sensors, we can identify where the problem is immediately. Using a good custom label on that device tells us where it is. And then we can track how it's spread by tracking how it advances through the building. And then we have real-time status information because the sensor and the control unit are basically communicating quite frequently. So here's where we start with TrueAlarm concepts. The major benefits of having addressable analog smoke sensors is it provides environmental compensation. What does that mean? That means as the environment changes, the smoke sensor adjusts to compensate for any changes. So if there's an accumulation of dirt occurring in the smoke chamber, then the smoke will adjust accordingly, therefore providing consistent sensitivity. We do have a self-test that's happening live in real time. So that's where the sensors communicates to the control panel, and it is talking to the control panel as if to say, okay, this is how my environment is changing, and the control panel makes a decision of whether that is normal or not, right? And then the last thing here is maintenance reminders. So that would be when the smoke chamber is gradually building up with some kind of an accumulation, we can report a dirty trouble, right? And then the technician can go out and either replace it or clean it. So how does this sensor do it all? Well, the sensor head has an analog value that it passes to the base, and then it converts it to a digital signal, and it transmits that digital number to the control unit, the CPU, and it will analyze that number to see if that number is crossing the threshold and is going to be an alarm or not. So this is where we talk about a conventional smoke and how does that work? Well, it depends what kind of conventional smoke you have. In this case, the first one, if you're looking at the part numbers here, A40989602, that's a TrueAlarm conventional detector with TrueSense. So with that type of head, we have the same built-in TrueAlarm technology to do adjustments on the fly based on the environment. But if you have a standard conventional detector from, years ago that doesn't have the TrueSense technology, then the illustration with the chart showing the comparison over time, That's saying that if you had dirt accumulation over time, if it reaches the threshold, it's going to go into alarm. It's not going to know that it's dirty versus it's a real fire. So here's some of the environmental factors we talked about on a couple previous slides that the TrueAlarm technology guards against. So as we said, if there's dust or dirt that's accumulating in the chamber, it will self-compensate. Temperature change, it might affect an older conventional, but it's not going to affect a TrueAlarm sensor quite as much. The same thing with humidity, voltage fluctuations, and when components degrade. These are all conditions that would cause an older conventional detector without TrueAlarm sensing to possibly go into alarm. So what else is good about addressable sensors with TrueAlarm is that we can individually program them for their own sensitivity. It's field selectable using the ES panel programmer. So the technician could program an individual device for a different, sensitivity versus maybe a group of them. And we could even flip-flop the sensitivity between the day and the night. So we could say, well, while people are in the building, I want my sensitivity to be normal, right? When the building's unoccupied, we write a program that says, okay, I want the sensitivity to be more sensitive at night when nobody's around. So we can do that as well. So what are the sensitivity levels? Well, with TrueAlarm, we can start with 0.2, which is highly sensitive, all the way to 3.7, which is less sensitive. What's the default? The default is 2.5, which goes with NFPA 72's, we'll call it normal setting. But check with your HJ, it may be different in different jurisdictions. It's typically 2.5%. So what about heat sensors and their default settings? Well, a radarized heat detector is the default setting is 15 degrees rise in a minute. Will put the system in alarm. If it's a fixed temp heat, then when the temperature reaches 135, it's going to put it into alarm. You'll notice there's other options like 20 degrees per minute or 117 degrees, 155 degrees. Those can be programmed. The defaults are in red, and the other values can be programmed should you need to set them for those. And in the center of this slide, we're just showing you that this is what a typical equation would look for a technician when they have to be off the default and on something else. He would write an equation that looks something like this, which we have another instructor on board today that's live who's going to be presenting how to program these settings that you see on this slide. So on this slide, we're analyzing how an alarm is determined based on a scale. We call it an analog scale. So how this scale works is you can see a gap here. You have your average number, which is 70 in this case, and then the threshold number, which we call the alarm threshold, is set to 138. So we have a gap of 68 analog units. Picture it this way. 68 analog units equates to the smoke sensor being set to go into alarm when the obscuration in that chamber reaches 2.5%, which is default. So let's say the HJ says, I want you to make these smokes in the computer room 0.5%. Well, picture that scale being reduced to your threshold number being like 85 for a alarm threshold. So now you only got a gap of 15 analog units. So that's how this scale works, is based on how sensitive it's set to, the gap either shrinks or it expands. So how does the control panel determine if it goes into alarm? It's basically comparing the actual value, which is the instantaneous value, to the average over time to determine whether it's an alarm condition or not. Once it determines it's an alarm, it activates the LED to a solid state. So normally it's flashing. If it's an alarm, it's going to be on solid, right? That same LED will be on solid if it's in a dirty condition as well. So the other thing to wrap into this is you can see the UL window is 0.5% to 4.0%. If I go back a slide ago, notice that we can operate outside the UL window in a good way, meaning we can go down to 0.2% for highly clean areas like computer rooms or medical areas. So we can operate between 0.2 and 3.7. So here's the same slide. The difference here is we're kind of talking about, one is when a technician installs a system and they're ready to get a final checkout by the fire department or the insurance company, they usually ask that that system be up and running for a day or two. And as you can see here, our top topic is average value. It says it's calculated over the previous 34 hours after the first minute of operation. So it takes about 34 hours for all the smoke sensors to have what I would call a solid average value. The other, I'll say, important items in this slide are how does the sensor communicate to the panel? I guess communicating that this smoke is has too much accumulation in it and it's getting dirty. Well, there's set points. If the average analog value equals 120, it reports a dirty trouble. If the average value reaches 135, it reports an excessively dirty trouble. And then there's another option for the technician to turn on what we call a pseudo point. And when that's turned on, it lowers the threshold to 110. And so it captures all the smoke sensors between 110 and 120. And then we can go and clean them or replace them before a trouble even happens. So that's a nice feature. So the other thing to remind you about is when it reaches the first dirty threshold, which is 120, it's going to cause a trouble on the panel. It'll be sounding the piezo, and the LED on the smoke itself will be lit. So it's going to notify the customer something's wrong, and then they're probably going to call a technician in, and they're going to go down the hallway looking for that smoke where the LED is lit, and they're going to take care of the problem. So here's another scale. It's similar, but as you can see, there's I call like a sliding scale, right? So what we're showing here is we have a gap, and it's between 70 and 138, just like the previous slide. So that's showing that there's a gap where this smoke sensor is programmed to cross the threshold when it reaches 2.5%. Well, over time, the same smoke sensor, maybe a few months later, it could be a year later, it's starting to accumulate a little bit of dirt. Well, when that happens, the bottom threshold number goes from 70 to 115 in this example. Well, what happens to the threshold number on the top? Well, it also advances from 138 to 183. This is what we call self-compensation, so that this sensitivity is constantly maintained. So what happens when it advances again? Well, now our number advances to 120 for an average, and the threshold it needs to reach to go into alarm is 188. What also happens when it reaches 120? Well, it enunciates a trouble on the panel, and somebody has to come and acknowledge that. What if it keeps advancing because somebody acknowledged it, but maybe a technician couldn't get there right away, and maybe it's been a couple of days? Oh, it went to 135, which causes an excessively dirty trouble. So now it reminds the customer, because now it's sounding the piezo again, that we need to take care of this, right? So it's these constant reminders that help keep the system running properly. So now, when the smoke in the chamber goes from, in this case, if you look at the left chart, it goes from 70 to 138 immediately, that's going to go into alarm. So when it's gradually moving up, it may put a dirty trouble on the panel over time. But if it's an immediate rise from 70 to 138, well, then it's going to be an alarm. In this case, if you were at excessively dirty, it would still need to advance by 68 analog units. But if it did it immediately, it would the same result. You're going to have an alarm on the system. So what about some other TrueAlarm addressable ID net devices? We have manual pull stations, smoke sensors we already talked about. We have an individual addressable module, which we like to refer to as an IM. And we're going to talk about these a little greater later. We have a relay addressable module, which we like to call a RIAM. We have a zone addressable module, and we have a duct detector as examples. What we chose to do is to blow up a diagram, a wiring diagram, of how a typical zone adapter module might be used. So in this illustration, we show 24-volt power loop is tied to terminals 1 and 2 to provide power to this device. And then terminals 3 and 4 would be your ID net addressable loop. And then on terminals 7 and 8, we just have a hardwired conventional circuit that can monitor dry contacts. In this particular example, it's monitoring a tamper switch and a water flow switch. And it's an we'll call it a specific configuration of resistors to do what we're going to talk about a little more later. We're going to talk about T sensing. So in this slide, we're kind of focusing on the loop distance guidelines for IDNet, Class A, and Class B, which the distance is 2,500 feet max. So it can be in either direction, right? If you'll see that it goes clockwise or counterclockwise, depending on if there's a break or not. So in this case, with a Class A, the 2,500 foot limit is the entire run, which leaves the panel and returns to the panel. So where the center smoke is, would be like the 1,250 foot limit, right? If it was a Class B, like in this case, then it would be 2,500 feet to the last smoke. Depending on which direction you're going, it's still 2,500 feet. In this example, we're saying that you could have 4 branches of T-taps, 2,500 feet each, and you can't exceed 10,000 feet total. So you couldn't add a 5th branch at 2,500 feet because that would be exceeding the wiring spec guidelines for IDNet. So here's an example of isolation for IDNet. And what we're showing you here is we have 3 loops. And we're showing on-board isolation, when I say isolation, electrical isolation between the 3 loops. So if the center loop got a short, it wouldn't affect the expansion loops below. If you got a short, so well, let me back up. You also have field mountable isolators as well. If you look at the left loop, you have 2 isolators in the center of this Class A loop. So if you had a break, we'll say between the 2 isolators, you would lose those devices between the isolators, but the isolators coming back to the panel would still be working. They could still talk to the panel. And that's the whole purpose of using isolators, is to electrically protect the circuit from shorts. In the center loop, we're showing you that we have smoke bases that also, you can order them as isolator bases. And they perform the same function and operation as a field mountable one. So here's a few of the most common IDNet devices. In this slide, we have a TrueAlarm analog sensor. Part number is A40989714. So that's the smoke head. And then the standard base that it's mounted to is an A40989792, right? So a building's typically going to be, have a majority of these devices in them. If it's a dorm room type building or a sleeping area, some kind of a residential area, well, you might have the A40989794. You might have a great population of sounder bases. But the same head plugs into either base. And then we also have another sounder base that can produce a 520 hertz tone to meet the requirements of sleeping areas. And all of these sensors have the multi-stage sensitivity selections that are available by programming them for which one you want. Just got to check with your HJ what's permitted. So here's a couple examples of what we call combination devices. And we call it a multi-point analog sensing because we can do multiple events from one device. So it's called TrueSense early fire detection, and we're going to get into that in a minute. So what do we see on the left? On the left, we see, or top left, we see a smoke head with a thermistor attached to it. So that's really a smoke heat. And it's mounted in a standard base. Could that same smoke heat head be mounted in the base on the right? Sure. Base on the right is actually a 520 hertz sounder base with a CO cartridge. So that's quite a device right there. You got a smoke heat combination, and you also have a CO sensor, and you have a sounder. So having the multi-sensor TrueSense detection is a competitive advantage, because now we can get an earlier fire warning through the correlation of the thermistor and the smoke working together. So in this slide, we're talking about two different types of heat sensors, one being a standard heat and the other being a high temperature heat. They do have defaults, and they're both programmable off the default settings, and they're self-restoring. So let's take a look at the I'll call it the non-high temp heat, right? Just a straight out rate of rise temperature heat. The default would be 15 degrees in a minute. Could be programmed for 20 degrees in a minute, Fahrenheit. The fixed temperature default would be 135 degrees, but could be programmed to do alarm threshold at 155. And the high temperature heat could be programmed to alarm the panel at 200 degrees or 190. That's another setting that's not shown. The other thing that these heat sensors can do is they can provide warnings for when the temperature is getting too cold. So it might be protecting an HVAC system from freezing. So when the temperature gets to 35, we may cause some kind of an annunciation at the panel to let you know that something needs to be done about that room before it freezes. So in this slide, we're talking about the individual addressable module. What is it? What's its purpose? Well, it monitors dry contacts for one, and they could be sprinkler devices as shown in this example, a tamper switch and a water flow switch, which are just conventional devices, but the individual addressable module has an address. So if one of these contacts closes, we're going to get either a trouble, a supervisory, or an alarm at the panel, but it's going to be reporting the address of that ID net, IAM, we call it, right? What are some of the specs? Well, as we can see here, it says total wiring distance from the IAM to the end of line resistor is 500 feet. It's a pretty good stretch. We do have some over voltage protectors for outdoor wiring or noisy applications. And the other spec on this is it's for indoor locations up to 158 degrees, where you might see this in an attic, right? So they're pretty sturdy devices for how small they are. And we have what we call T-sensing operation. What is that? Well, it can detect obviously normal, which is the circuit's wired properly and there's no compromisation of the circuit, or it's an open where maybe somebody didn't tie a wire down, or maybe somebody cut the circuit. We're going to report an open, and then it can detect whether it's a short or a current limited based on this resistor configuration. So if switch A closes, we're going to get a short, which is going to cause an alarm on the panel. However, if switch B were closed, it's either going to report a supervisory or a trouble because it's not a dead short. It's actually shorted through the 1.8K resistor, and the panel knows the difference. So that's a pretty fantastic wiring scheme to provide monitoring of two devices with one addressable module. It's ideal for dampers in a hospital, for instance. You might have, quite a few dampers above the ceiling for the HVAC unit. And then the other one is, of course, the sprinkler system devices that we just talked about. So this device here is a lot like the previous device. It's an IAM with a relay attached. So it's doing monitoring and control out of the same device. So we'll say that the smoke in this case crosses the threshold, and that smoke is located in the elevator equipment room. And we want to exhaust any smoke that could be in the shaft. Well, when the smoke in that location alarms the panel, it tells the relay IAM to activate its relay to control the exhaust fan and exhaust the smoke from that area. And that's like a typical use of a relay IAM. We also use them for elevator control, for primary, alternate, and shutdown control. Here's an illustration of a zone adapter module with two 4-wire conventional smoke detectors. On the left, we have the 24-volt power circuit because they're 4-wire smokes. We need power for them. And then we have the IDNet loop, which gives this module an address. And the 4-wire sensor loop is on the bottom right. So what happens is 4-wire smoke, we'll say it goes into alarm, it latches in, and the zone adapter module reports an alarm to the panel. So somebody does a reset because they find out that it's the smoke is clear and the fire was put out quickly or something. When they perform a reset, it drops the 24 volts to unlatch the 4-wire device. So a typical example would be a retrofit where, there are old smokes that use this technology, and we can just put in some zone adapter modules to start to migrate the facility to an addressable system. And when the customer's ready to change out these old devices to maybe some addressable ones, then we tie them directly to the IDNet loop. So we also have duct sensors with TrueAlarm technology. It's got a visible cover so that, we could do inspections really easily, visual inspection. And we have 3 different LED plates. We have a standard LED plate that you would probably mount on the ceiling or the wall below, wherever this duct smoke is. Then you have the one in the center, which has a key switch to test it. And we have the one on the right, where if it was a full wire duct smoke, you have a power LED and an alarm LED. So those are all available as options. So at this point, I'm going to turn it over to Mr. Dave Henry, who's going to give us a brief demonstration of how these devices can be programmed in the AutoCall programmer. And he's going to give us a brief explanation before he does that. So Dave, I hand it to you.
Okay, thanks you, David. Now we're going to talk about the ES Panel programmer, how to put these IDNet devices in there. A couple of things we need to know about a piece of equipment. First of all, is a device type. Device type is the physical piece of equipment. So here's some examples. If you have a photo, a fixed temp heat, a rate of rise heat, or a combo, we have different device types for that. So fixed heat, rate of rise, and combo. If these are in standard bases, that's all you're going to use for the device type. But if we use non-standard bases such as isolator, we're going to put a letter I in front of those. If it's a sounder base, we can use S or T in front. If it's a relay base, we can put R in front. And if we use MCO, that would be for a CO base. If you don't match up the hardware with what you program, you will get a wrong device trouble on the panel. The second piece of information is the point type. Point type is how is that piece of equipment applied? How is it going to act? Are you going to get fire LEDs on the front of the panel? Supervisory? Trouble? For example, David mentioned the 4-state for the T-Sense for the water flow tamper. So we can get 3 different LEDs depending on the conditions coming back. Also, when you look at the point, to the bottom left of it is going to tell you the point type. It'll say water flow, tamper, addressable pull station, things like that. So you don't have to use the device description in your 40-character label. Selecting the proper point type will automatically do that for you. Here's some examples. If we use a photo of smoke, what type of condition do you want to see on the panel? Most of the stuff you're going to use is just a smoke point type. If you want to use a V smoke, a verified smoke, all that's built into our software. It's the same hardware, just change the point type. If it's mounted in a duct sensor, use duct. You may want a priority 2. What if the smoke is in a college dormitory room? You're probably going to want a supervisory, or you can actually use a latching supervisory if you so choose. So these are examples of the different point types you can use if you have a photo smoke head. So when we go to the programmer, you're going to take and select a point. In this example, M1-1. We'll go down here in the drop down and we'll select the device type and the point type and put a label.
Dave, the slides aren't changing for us.
I'm sorry. I did not share my screen. Is that better? Can everybody see that now?
Yes, thanks, Dave.
All right, sorry about that. All right, so again, device type was physical piece of equipment. Next, here's some examples of device types. So standard photo, a fixed temp heat, a rate of rise heat, a combo smoke heat. These are examples in a standard base. If we use different types of bases, such as isolator, we'll put a letter I in front. If it's a sounder base, we can use S or T, and those have different characteristics of operation. If it's a relay base, we can put an R in front. If it's a CO base, we would have MCO in front. So what you want to do is make sure when you select the device type, it matches the physical piece of hardware out there. Next characteristic is how is the point type? How is that equipment applied? How is it going to act? What's it going to cause at the panel? Is it going to cause a fire, a supervisory, a trouble? For example, David mentioned the flow tamper combinations. We can get 3 different LEDs at the panel relative to the conditions. So the flow would be a alarm, a fire. The tamper would be a supervisory, and a fault on the wiring would be a trouble. Just below the 40 character label for the point to the left side, you'll see the point type description. Water flow, tamper, pull station, smoke detector. You don't have to use that information in your 40 character label because the point type helps do that for you. Here's an example of a photo smoke in a standard base with all the possible point types available. Most of your stuff you're going to use is just smoke. That's a standard fire alarm point. You may use verified smoke, uses the same piece of hardware, it just acts differently in the software. If it's in a duct housing, you would select duct. A few other examples would be, for example, a college dormitory. You might take and put supervisory. So if the students burn popcorn in their dorm room, they'll set off a supervisory. And you can also make that a latching supervisory. So these are some examples of point types that are available to pick. When you get in software, I'm in the IDNet card, and we'll actually go in the programmer in just a minute here. Here is the IDNet point. We've selected M1-1. Go down here and change it from unused to the device type needed. Give it the appropriate point type and a 40 character label. So let's go to the programmer. I have the programmer open. I'm going to go to the IDNet card in the hardware tab. We'll go to point editing. I'm going to select the first one, M1-1. And down the bottom again, you'll see device type, point type, custom label. There's 2 ways you can find the device type. You can either hit the scroll down here and slot. You can drop down and scroll up and down, or you can just start typing it. When the text is blue, you can just start typing it. I'm going to use a photo here. So I'm going to just type P, and when you find PH, all you have to do is hit tab, and it put photo. The next part would be to change your point type if needed. So let's give this a name here. This is going to be bedroom 203. And we like to take and put the point name at the end of it because this helps troubleshooting later in the alarm and trouble logs in the front display. So we put the point name, put the cursor to the left of the point name, and hold the spacebar down and push it all the way over. Let's look at some other different device types. Pull station. Now you might think pull station starts with a P, but in our hardware, it starts with ADR for addressable pull station. Point type is pull. Can be used for other conditions, but pull. I'm not going to fill all the labels in for now. I'm just going to put a bunch of hardware in. Other things David talked about was an IAM. So again, up here, I can highlight the unused on the next one and just start typing IAM. This is where you have the ability to pick several different things. I could pick a combination water flow sprinkler tamper down here, and I would have 2 things on one circuit then. How about a relay IAM? A relay IAM starts with R, I, 2 letters and found it. How is this being used? Is it being used for air handlers, alternate elevator recall, door holders, primary recall for an elevator? Is it going to be for the elevator shaft shutdown? So we have a lot of different options here. Let's actually take and make a water flow relay on this one. Another example. How about a monitor exam he showed? So monitor exam starts with M, and we have a Class A or a Class B. So if I leave it A, it's a Class A monitor exam. If I select B, it's monitor Class B. Again, make sure the piece of hardware you have matches what you program so you don't get wrong device. And then we can program this as generic fire, or we have all sorts of options in here. We could actually do a fire pump monitor if we chose. Duct sensor, well, duct just falls under photo, and then we would select duct. Let's pick a fixed temp heat. So we're going to type heat. The next one, I'm going to do a rate of rise heat. So I'm going to do O heat. And again, if you hit the drop down, you can see the descriptions on them. The next one, we're going to do a high temp heat. So HT for high temp heat. So these are a bunch of examples. One more I'm going to put in here is called a combo. So a combo, this would be in a standard base. Combo has subpoints, so we have a 0 for the unit. You notice it's utility point type. So the unit itself doesn't report anything other than head missing or if it's talking. The subpoints, -1 is the photo smoke part of it. -2 sub part can be a fixed heat, or down here I could change it to a rate of rise heat if I wanted. And then here's our correlation point. So you assign each of the subpoints. When you leave the 0 as utility and select individual things like smoke heat, what you get is the individual conditions coming up on the panel. You get smoke detector or heat detector individually as the sub address. All right, I'm going to click OK. We'll go to custom control. In a custom control, we have some sample equations. I've created some equations just by label. So we're going to do some examples here. So we'll set heat rate of rise to 20 degrees per minute. Over to the right, we're going to click on End Inputs and Add to start our programming. We do have a startup pseudo that's easy to use, and the point becomes true as soon as the panel finishes starting up. So point status, or we don't need to worry about that on the first gate, so we don't need to select one or the other. We do not need to select not in this example. A34 is our point. We're going to actually type on. So A34, although it's an analog pseudo, does have an on state as well. I'm going to type A34 here in the point name. Don't put a space, it doesn't like it. You could have also picked on tag list. And because I already typed A34, we'll see the tag came along and was system startup pulse timer. So that's the same in all of our systems. You could have also used the filter or the search to look for the word startup. And click finish. So what's going to happen, our input's going to be true as soon as the panel starts up. So when you get to the point and the troubles and you start acknowledging, that's when A34 comes on temporarily. So this equation said we're going to set the rate of rise heats to 20 degrees per minute. So I put my cursor on end outputs. I'm going to add an output statement. And here we're going to select an opcode called set rate of rise heat sensors. Click next and tell it what temperature you want. So we have Fahrenheit and Celsius. And in this example, we wanted to change it to 20 degrees in a minute. When you click next, it asks for a point, or you can click on tag list. All the available heats that have rate of rise function will be shown right at the top here. You'll notice we only have one right here. This device type is an O heat. The fixed temp heats don't show up here. After you highlight it, make sure you tag it with the spacebar and click OK. So this example, I'm setting the rate of rise heat on M1-8. Next equation, it'll be very similar. We're going to use the same input. So again, I'm going to click on end outputs and we'll do point status. Nothing needed here to change. The on state of A34. Our output in this example, we're going to take and add an output. And instead of setting the rate of rise, right above it is select alarm threshold smart sensor. Click on that. Tell it if you're setting the smoke or the heat characteristics, in this case heat. Next, and we can change the temperature here. I'm going to select 155. Click next. Again, I could type the point if I know it, or the tag list will help me, and it'll show me all the heats that can go to 155 degrees. So I'm actually going to pick the sub point for that one combo sensor we did. So that's M1-10-2. I'm going to select M1-7. And you can also change the fixed temp on a rate of rise heat, in this case M1-8. Now, because I've selected 3, when I click OK, it asks me if I want to create a list. At this point, I could click yes, and it would become a brand new list. But I'm going to click no this time. You'll see only one of them shows up here. But here's the magic. When you click finish, it puts 3 separate outputs for me here. If I had created a list, instead of M1-7, for example, it would be L256. It would be the next available list. So you can program it either way. Let's look at a high temp heat. Now, I'm going to do something a little different. I put my cursor to the right of inputs, and I hit the Enter key. If you get good enough, you can actually start typing the stuff out here. So we're going to type status on A34. When I right-click and click Parse, it's going to validate all that for me. So this is the same way we did it through the ad. So if you know how to type it, you can actually do it right there. Let's go add an output. And this time we're setting a high temp heat. So it's set alarm threshold smart sensors again. Remember the last thing we did. Heat. And I'm going to select 190 this time. In the tag list, you'll notice it only gives me a device type that's an HT heat. So the software knows if a different point device type can go higher or lower in temperatures. And click finish. So now we've set a high temp heat M1-9 to 190 degrees. The default was 135, by the way. Smoke sensor sensitivity. We're going to do the same thing. We're going to type our status on A34. I'm going to click down on the end outputs and add. You notice back there, it automatically filled the information in for me, the rest of A34. Set alarm threshold smart sensors. This time we're going to set smoke. If you want to set it higher or lower than the default 2.5%, we can pick it here. So let's say we want it more sensitive at 2%. Click next. There's a default list in the software called L76. Now, L76, I'll click the tag list and show you. It's the variable sensitivity photo analog sensors. Every time you put an analog smoke in here, it automatically goes in that list. So there's no then, but if you wanted to pick individuals or create your own list, you could do that as well. And click finish. So now you're thinking, Dave, you wrote 4 equations that all have A34 for a start. Couldn't I have put all those outputs in one equation? I could have. So although because they don't all use the same input start and that's it, you could have put all these outputs in one equation. That would work fine as well. So that's the end of our demonstration of the software. We'll now turn it back for any questions. So questions, there's 2 ways you can ask questions. You can either turn on your microphone, as Brian mentioned earlier, or we also have a raise hand function. The other option is you can open the chat and type in there.
Thank you, David. We welcome your questions now from any of the participants. Okay, we have a question in the conversation chat. We have one from Ben. And the question is, if you acknowledge the dirty trouble and silence the piezo, will the piezo sound again after a 24-hour period if the sensor has not been cleaned?
The condition there, Ben, is by default, we have a trouble reminder in the panel. The trouble reminder by default turned on is an 8-hour setting. You can set it to a maximum of 12 hours. We do not have a 24-hour reminder. We have a maximum of 12-hour reminder on there, so that is doable.
Thank you, Dave. Are there any questions from any of the participants? Please go ahead and unmute your microphone and ask your question.
Can you hear me?
Yes, we can. Go ahead with your question, sir.
I have a question about the walk test mode. Normally, when you put the system in walk test, you can go around test all devices, and the system does not send any signals to central station. Is there a way to make it so that it will still send signals to central station?
Well, that's a very good question, and I think what we'll have to do is to document that question and then get back to you. So if you could just send me a message in the chat window to identify yourself, and I'll be sure to get the answer back to you and circle back with all the participants.
All right.
Are there any other questions from the audience? If there are, please unmute your microphone using your mouse and the control bar.
Yeah, this is Larry. I just wanted to say that he was just talking about the walk test, and it was very muffled, so we could not really hear the question.
Well,
Larry, the question on that was, when it's in walk test, it doesn't send anything to the central station. Is there a way you can set it up to do that? We don't have the answer off the top of our head, but Brian is going to research that once he gets the typed question in chat.
Very good. Thank you.
You're welcome.
thank you for that, Larry. Much appreciated. Are there any other comments or questions from the audience?
Yes. Is there a way when you have the entire program in, is there a construction mode so you can enable and disable points that may or may not be installed?
Yeah. Yes, there is. There is a feature called install mode that we have in our software. So you can take and pre-make lists, for example. Maybe you do a 10-story building. You can make a list for each of the 10 floors, and you could put each of the floors into install mode. While it's in install mode, it takes and hides all the no answer and missing devices that are disabled. It hides them all behind a single trouble, and the single trouble will stay install mode active. So you don't have to muddle through 400 troubles while you're working on the system. You could take each of those lists per floor and put them in and out of install mode anytime you want. It's a very nice feature of our panel to do that. So that way you don't have,
you do
Go
that
ahead.
through the software?
Two things. You can create the lists pre-configured in the software. The other option is if you're on site and you didn't create the list, you can put all the no answer devices into install mode at one time. Right? But it's not selective. It just says everybody who's no answer. Another thing is when you're trying to take them out of install mode, you can say everybody who's normal come out of install mode.
And
So
you
we
can
have
do that from the front face?
That's from the front face, right?
Yep.
Or if you do pre-program the list by floor, you can take and call the list up from the front panel and put those in and out. So you don't have to keep doing program changes every time. You can pre-configure the job ahead of time and keep working through all 10 floors without having to keep dumping a program in every time.
Excellent. Thank you.
Sure. Thank you for that question, Cameron. And I'd like to add to that, and that is if you go into log into Navigator, you'd be able to see one of the selections next to Selection Navigator is Training. And if you click the training link, it's going to bring you to our private YouTube type channel called ULearn. And when you get to ULearn, you'll see that there are technical videos there. There are several that describe exactly what David Henry is talking about with that installation mode. There are explicit videos for the technician on how to set up those lists, how to identify those points, and then for the user, how to take them in and out of install mode using the front panel interface. So I would like to have you go over to Navigator and then selecting the training. And then that will log you into ULearn, where you'll find all those videos. And I think as of today, there are about 66 up there. I think there are. So feel free to peruse up there. You'll see the first set that we put up there initially were for that install mode operation.
All right. Thank you.
You're very welcome. If anybody else has a question, please unmute your microphone using the control bar and go ahead and ask your question. Okay, so it looks like that there are no longer any questions. So I would like to thank everybody. Wait a second, there's something coming in on the chat window here. Here's a question from the field, and it's, is there a way to have system and sensing? Oh, no, this is the question that he wants us to answer. Okay, so we'll get back to you, Ben, on that and the rest of the group. So thank you very much for coming today. We very much appreciate your attendance in this series of webcasts. On behalf of my colleague, David Govin and David Henry, I'd like to bid you a great afternoon and give you back the rest of your time for your day. Thanks very much and have a nice day.